In 1957, two astronomers in Mexico photographed a single violet point of light and filed it under a number instead of a name. Braulio Iriarte and Enrique Chavira were surveying faint blue stars from the Tonantzintla Observatory. Entry number 618 looked like all the others on the plate. A faint star, oddly violet, probably a white dwarf. Nothing left to explain. 13 years later, in 1970, a radio survey in Bologna pointed a different kind of instrument at the same coordinates and found something a dead star has no business producing. Steady stream of radio emission. Dead stars don't do that. It took 6 more years to find out how wrong the file actually was. In 1976, astronomer Marie-Helene Ulrich turned a spectrograph on the object at McDonald Observatory in Texas. And the spectrum she got back didn't belong to a star at all. The light was redshifted so far that the only honest explanation was distance on a scale. Nothing in the Milky Way could produce. The number she calculated meant this light had left its source when the universe itself was less than 3 billion years old. A dying star nearby had become an entire galaxy's engine, photographed from a point in time before Earth existed. You already know one number from this story, even if you've never heard of Tonantzintla: 66 billion times the mass of our Sun, the black hole at the center of what astronomers now call Ton 618, the number that's supposed to make it the single biggest, scariest black hole ever measured by anyone, anywhere. Here's what that number actually is, and isn't. It was one measurement, using one sliver of light, taken in 2004. 15 years later, a second team measured it differently and got an answer nearly half the size. And there's a third black hole in a different galaxy that may already outweigh both. Nobody has ever actually seen this thing. Every fact tonight comes from light bent and stretched across 10 billion years. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Start with what a quasar actually is, because supermassive black hole undersells what's happening at the center of Ton 618. A black hole itself gives off no light. That part is almost the definition. What makes Ton 618 one of the brightest single objects ever detected is not the black hole. It's everything falling into it, gas and dust, pulled in from the surrounding galaxy. Don't fall straight down the way a dropped stone does. They spiral. The way water spirals toward a drain, collecting into a flattened, furious disk that orbits the black hole at a meaningful fraction of the speed of light. Friction inside that disk, particles colliding with particles millions of times a second, layer scraping against layer. Heats the material to temperatures of hundreds of thousands of degrees before it ever crosses the point of no return. Superheated gas radiates. That's the whole secret. Ton 618's accretion disk, the ring of infalling material orbiting its black hole, has been estimated to shine with a luminosity near 140 trillion times that of our Sunday, an absolute magnitude of roughly negative 30.7, bright enough that if the entire disk were placed where our Sun sits now, the extra heat alone would end every form of life on Earth within the first few seconds. And this is light from an accretion disk alone, a structure a single light-year across, dwarfing the star system that built it, without needing the black hole itself to shine at all. Set that number against something familiar. Our entire Milky Way, every one of its roughly 200 billion stars combined, produces something on the order of 20 billion times the Sun's own light output. Ton 618's accretion disk alone, a structure smaller than the gap between two neighboring stars, outshines that entire combined galaxy, every star in it, all at once, by a factor of several thousand. That's the part worth sitting with before any of the numbers get larger. The most extreme, most violent, most energetic object in this entire story isn't the monster. It's what the monster does to what falls near it. Ton 618, whatever its exact mass turns out to be, has never once been seen directly. Every photon that ever reached Ulrich's spectrograph, or any instrument since, came from the disk burning around it, light thrown off by matter in its final moments. Before crossing a boundary, no light can cross back over. There's a second casualty of that same glare. Easy to miss the first time through this story. The galaxy Ton 618 actually lives in. Every quasar sits inside an ordinary host galaxy, full of ordinary stars, the same way our own Milky Way surrounds its own comparatively quiet black hole. In Ton 618's case, that host galaxy has never been directly studied because the quasar burning at its center outshines it by a margin large enough to make the surrounding starlight functionally invisible from Earth. Imagine standing next to a lit flare on a dark field and trying to make out the color of the grass beneath your own feet. The disk isn't just the brightest thing in the picture. It's bright enough to erase the picture's background almost entirely, which means an entire galaxy's worth of ordinary stars, planets, and, for all anyone can currently rule out, quiet, unremarkable solar systems sits hidden behind the glare of the very engine devouring its center. There's a tempting shortcut worth heading off before it takes root. The idea that Ton 618's redshift simply means the object is moving away from us very fast. The same way a receding ambulance's siren drops in pitch. At this distance, that sentence stops being accurate, and understanding why matters for taking the rest of tonight's numbers seriously. An ordinary Doppler shift, the kind used moments ago to explain how a spectral line's width reveals orbital speed, describes something moving through space, relative to an observer also sitting in that same space. Ton 618's redshift is a different phenomenon entirely, called cosmological redshift. The space between here and Ton 618 has itself been stretching, continuously, for the entire 10.8 billion years. The light has been crossing it, carrying the light's wavelength along for the stretch, the same way a drawn-on wave stretches if you pull the rubber sheet it's drawn on. Ton 618 isn't racing away from the Milky Way through fixed, unchanging space. The space itself, between here and there, has been quietly growing the whole time. The distinction isn't pedantic. Try to convert a redshift this large into an ordinary recession velocity using the simple, everyday version of the Doppler formula. The resulting speed comes out faster than light itself, a nonsensical answer, and a clear signal that the everyday formula has been pushed well past where it's allowed to work. Cosmological redshift, treated correctly, never violates the universe's speed limit, because no single object is actually moving through space faster than light. What's expanding is space itself, carrying galaxies apart the way raisins in a rising loaf of bread drift apart from each other without any individual raisin doing the moving. Ton 618 is a reminder that even a concept as familiar sounding as redshift stops meaning quite what it means nearby once the distances involved get large enough to make the universe's own expansion part of the OA. Story. There's a number sitting quietly inside all of this that deserves to be unpacked properly before the mass question takes over, because it will resurface more than once tonight, and it's easy to state carelessly. A redshift of 2.219 describes how much the universe's own expansion has stretched Ton 618's light on its way here. Not a speed, and not, by itself, a distance, but a ratio. Exactly how much longer each wavelength has become compared to when it left home. Turning that ratio into an actual distance takes a choice, because distance, for something this far away, stops meaning one single thing. The light travel time distance, literally, how long the light has been traveling, comes out to roughly 10.8 billion years. But the universe has kept expanding for the entire length of that journey. carrying the space between here and ton 618 outward the whole time the light was crossing it, so the object's actual present-day distance, called the co-moving distance, is considerably larger, something closer to 18 billion light-years, even though the light itself only needed 10.8 billion years to arrive. Neither number is a mistake, and they aren't in conflict with each other. They're answers to two different, equally honest questions. How old is this light? And how far away is the thing that made it right now? Ton 618 is a reminder that at these distances, how far away is it stops being a single sentence and becomes a small negotiation about which kind of far you actually mean. Before moving to the number that is disputed, it's worth being precise about the one that isn't, because it would be easy, after everything already said about redshift and expanding space, to assume the whole story is built on shaky ground. It isn't. A redshift measurement doesn't rest on a single emission line the way a mass estimate does. Ulrich's original spectrum, and every one taken since, shows multiple different emission lines at once, each one a distinct fingerprint of a specific element at a specific rest wavelength. Every one of those lines, independently, has to shift by the exact same factor for a redshift measurement to be considered solid. And, for ton 618, they do. Hydrogen, carbon, and several other elements all point to the same figure, 2.219, cross-checked against each other, rather than resting on any single line's word alone. That kind of internal agreement across multiple independent lines is exactly what makes a redshift measurement trustworthy, in a way a single-line mass estimate never quite manages. So the distance to ton 618 and the age of its light are not the parts of tonight's story still being argued over. Astronomers agree, and have agreed since Ulrich's 1976 paper, on how far away this object sits and how old its light is. What remains genuinely unsettled is a completely separate calculation, built on top of that solid foundation. How much mass, at the very center of that agreed-upon distance, is required to explain the motion of the gas swirling around it? The uncertainty in this story was never about where ton 618 is. It has only ever been about what, exactly, sits at the middle of it, and how heavy that thing turns out to be, which raises an obvious problem. If the black hole itself is invisible by nature, how does anyone put a number on its mass at all? The answer astronomers reach for is called the virial method, and it works the same way weighing the sun works, just from a much stranger angle. You can't put the sun on a scale either. What you can do is watch something orbit it, a planet in that case, and use the speed of that orbit, plus the distance, to calculate how much mass must be doing the pulling. Gravity leaves fingerprints in motion. Measure the motion carefully enough, and the fingerprints tell you the mass. Around a black hole like the one inside ton 618, the orbiting material isn't a planet, it's the superheated gas in the accretion disk itself, and astronomers read its motion through the width of a single spectral line, a specific wavelength of light emitted by hydrogen, called hydrogen beta, that gets smeared wider or narrower depending on how fast the gas producing it is moving. Faster gas smears the line wider, slower gas keeps it narrow. Combine that velocity with an estimate of how far the gas sits from the black hole, derived from the disk's own brightness, and the mass falls out of the arithmetic. The same orbital logic used on planets, just applied to gas moving at a meaningful fraction of light speed, instead of a planet moving at a few miles per second. The method itself wasn't invented for objects this extreme. It was built and tested first on much closer, much better behaved active galaxies, where astronomers could watch a flare of light from the black hole's inner regions ripple outward and brighten the surrounding gas days or weeks later. A technique called reverberation mapping patient enough to measure the actual physical size of the glowing region directly, light echo by light echo, before ever trying to infer a black hole's mass from it. Those nearer, slower, more carefully measured systems are what calibrated the whole approach. They're the ruler every distant, unresolvable quasar, like TON 618, gets measured against. Once, from 10 billion light-years away, with no way to double-check the extrapolation directly. In 2004, an astronomer named Ohad Shemer and his colleagues ran exactly that calculation on TON 618's hydrogen beta line. The gas showed velocities into the thousands of kilometers per second, fast enough that only an extraordinarily massive object could be holding it in orbit at all. The number that fell out of the math was 66 billion solar masses. Picture what that number actually means before it gets treated as a headline. A black hole that size has an event horizon, the boundary past which nothing, not even light, escapes, with a radius of roughly 1,300 astronomical units, 1,300 times the distance from Earth to the Sunday. Neptune, the outermost planet in our solar system, orbits at only 30 of those same units. Scale our entire solar system up to the size of TON 618's event horizon, and Neptune's orbit would still fit inside it more than 40 times over, with room left to spare. This isn't a large star. It isn't a large galaxy's core. It's a boundary in space wide enough to swallow our sun and every planet that orbits it more than 40 times, before it even finished being large. For one more comparison, closer to home, the black hole anchoring the center of our own Milky Way, the one every star in this galaxy, including the Sun, quietly orbits, weighs a little over 4 million solar masses. 66 billion divided by 4 million comes out to something past 15,000. The black hole at the heart of TON 618, on the higher of its two disputed weighings, outweighs the black hole at the center of our entire galaxy by a factor larger than the number of days in 40 human lifetimes. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Before going further into what went wrong with the 2004 measurement, it helps to understand, concretely, what the width of a spectral line actually means, because the phrase can slide past without landing. Sound offers the clearest way in. A passing ambulance's siren rises in pitch as it approaches and drops as it pulls away. The Doppler effect. Sound waves bunch tighter by an approaching source and stretched thinner by a receding one. Light behaves the same way, just with color standing in for pitch. Light from something moving toward an observer shifts slightly bluer. Light from something moving away shifts slightly redder. Now imagine, instead of one ambulance, a vast swarm of them, all circling a single point at once, some moving toward you, some moving away, most somewhere in between. The combined sound wouldn't be a single clean pitch. It would be a blur, a spread of frequencies smeared across a range, wider if the ambulances are circling fast, narrower if they're circling slowly. A spectral line from a quasar's accretion disk is exactly that blur, translated into light. The disk isn't one object moving at one velocity. It's an entire ring of superheated gas, orbiting from every angle at once, some of it swinging toward Earth's line of sight, some of it swinging away. Instead of one sharp, narrow spike of color at a single wavelength, the combined light spreads into a wider or narrower smear. The width of that smear encodes exactly how fast, on average, the orbiting gas is actually moving. That's the entire physical basis. Underneath every mass estimate in tonight's story, measure the width of the blur precisely enough, in a wavelength precise enough, and the orbital speed. And from it, the mass required to hold that speed in orbit falls directly out of the arithmetic. It's a beautiful piece of reasoning, borrowed from something as ordinary as a passing siren and pointed at an object 10 billion light-years away. It's also exactly why the measurement is only ever as good as the blur it's built from, and why two different blurs, read from two different lines, were always capable of telling two different stories about the same monster. 66 billion solar masses sounds like an answer. It was never meant to be the final one. And the reason has nothing to do with sloppy work by Schemmer's team. It has to do with where, exactly, hydrogen beta ends up once light travels far enough to reach us from TON 618. Every wavelength of light from an object this distant gets stretched by the same redshift that told Ulrich decades earlier how far away this thing actually was. At a redshift of 2.219, a wavelength that starts out in the visible part of the spectrum, the part human eyes and ordinary telescopes handle easily, gets dragged all the way into the infrared by the time it reaches Earth. Hydrogen beta is exactly that kind of line, comfortable and bright in nearby objects. At TON 618's distance, it lands in a part of the spectrum that's harder to observe cleanly from the ground, crowded with the glow of Earth's own atmosphere and demanding instruments built specifically to work in the infrared rather than ordinary visible light. Ground-based infrared spectroscopy in the early 2000s was neither easy nor cheap. Earth's atmosphere glows faintly in the infrared all on its own, a background hum bright enough to bury a faint signal from 10 billion light-years away if the observation and the calibration aren't handled with real care. Every measurement of hydrogen beta at this distance carries that atmospheric noise stitched into it somewhere, a cost that simply doesn't exist for the same line measured in a nearby, unredshifted galaxy. None of that makes the 2004 measurement wrong. It makes it fragile in a specific, nameable way. A single line, observed in a difficult part of the spectrum, feeding a method that was always going to be sensitive to exactly how well that one line was measured. Astronomers doing careful work know this. It's why, 15 years after Schemmer's number became the figure, every article about TON 618 would eventually repeat. A different team went looking for a second way to weigh the same monster. In 2019, an astronomer named Shuer Ge and a team of colleagues reran the calculation. They reached for an entirely different spectral line, carbon-4, a line that starts out much further into the ultraviolet than hydrogen beta, and at TON 618's redshift happens to land conveniently back inside the range. Ground-based optical telescopes can observe without a fight. No infrared instrument required, no atmospheric glow to fight through. On paper, an easier line to measure cleanly than the one Schemmer's team had been stuck with. The gas traced by carbon-4 told a different story. Instead of velocities near 10,000 kilometers per second, G's team measured something closer to 2,700, still ferociously fast. Still far beyond anything found orbiting an ordinary star, but noticeably gentler than what Schemmer's line had shown. Slower orbital velocity implies a weaker gravitational grip, and a weaker grip implies less mass doing the pulling. Run the same virial arithmetic with the new number, and the black hole that had been 66 billion suns shrinks to something closer to 40.7 billion, not a small revision. A number nearly cut in half. Using a different line, from the same object, 15 years after the first number had already made its way into documentaries, trivia lists, and exactly the kind of video you're listening to right now. 40.7 billion solar masses is still, by any ordinary measure, an incomprehensibly large object, heavier, on its own, than roughly 2/3 of every star in the entire Milky Way combined. It simply isn't the same incomprehensibly large object the first paper described. And that gap, quietly, is where this investigation actually lives. Here's the part that keeps this from being a simple story of an old number getting corrected by a newer, better one. Carbon-4 has a documented weakness of its own, and it isn't a minor footnote. Quasars don't just accrete matter quietly. They also blow it back out. in violent outflows and winds, driven by the sheer pressure of radiation pouring off the accretion disk, streams of gas shoved outward at velocities that can rival the very orbital speeds astronomers are trying to measure in the first place. Carbon-4, as a line, sits unusually close to those outflows in the structure of a quasar's spectrum. Outflowing gas moving toward an observer can distort the line's shape in ways that mimic or mask genuine orbital velocity. A wind blowing outward can make gas velocities look slower than the actual orbital speed doing the real gravitational work, which means carbon-4-based masses carry their own well-known risk of running low for reasons that have nothing to do with the black hole's true weight. This isn't a flaw unique to TON 618's 2019 remeasurement. Astronomers studying quasars in general have flagged carbon-4 as an unreliable mass tracer for years, precisely because so many quasars show exactly this kind of wind-driven distortion in their spectra. Choosing carbon-4 wasn't a mistake. At TON 618's redshift, it was often the only practical line available to ground-based optical telescopes. But practical and trustworthy aren't the same word. The honest caveat belongs attached to the 40.7 billion figure exactly as firmly as the observational caveat belongs attached to the 66 billion one. So the honest position, as of the most recent reviews of TON 618's literature, isn't the old number was wrong and the new one is right. It's closer to this. One measurement uses a clean line in a difficult part of the spectrum. The other measurement uses an easier part of the spectrum with a line that's known to sometimes lie. Neither team made an error, both made a defensible choice. And both choices came with a cost attached that the other one didn't have to pay. Astronomers have not converged on which cost matters more. The 66 billion number remains, by far, the one repeated in popular science, largely because it arrived first and made for a better headline, not because the field has ruled decisively in its favor. Hold both event horizons in your head at once, because the comparison is worth making honestly rather than picking a winner by default. At 66 billion solar masses, TON 618's event horizon stretches roughly 1,300 astronomical units across its radius, more than 40 times the distance from the Sun to Neptune. At 40.7 billion solar masses, that same boundary shrinks to somewhere near 800 astronomical units, still more than 25 times Neptune's orbit, still a boundary that would comfortably swallow our entire solar system with room left on every side. Neither number is small enough to argue about in any practical sense. The disagreement between them, nearly a factor of 2, unresolved after 15 years of better instruments and more careful analysis, is itself the more interesting fact. It isn't a rounding error waiting to be tidied up by the next paper. It's a genuine, structural uncertainty sitting at the heart of one of the most extreme objects astronomers have ever tried to weigh. It has survived exactly as long as anyone has been paying close attention to it. Put the two figures side by side. One more time, in units a body can actually picture. Light takes about 4 hours to cross from the Sun to Neptune. Cross TON 618's smaller, more conservative event horizon at that same light speed pace, edge to edge through the center, and the trip takes something close to 9 days. Cross the larger horizon instead, and the trip stretches past 2 weeks. 15 days of travel at the fastest speed the universe allows, just to get from one side of the boundary to the other. Both numbers describe the same single object. Neither one has been retired, and still, set against a large enough ruler, even the bigger of those two horizons shrinks back down to something almost humble. The nearest star beyond our own Sun sits a little over 4 light-years away. TON 618's event horizon, at its largest disputed size, spans only around 4/100ths of 1 light-year, a boundary that would swallow our entire solar system whole and still occupy less than 1% of the distance to the nearest star. Enormous by every human measure, barely a rounding error by the standards of the space between stars. The word quasar itself carries a small, honest confession inside it, worth pausing on before this investigation moves further. When Martin Schmidt and his contemporaries first encountered objects like 3C 273 inches the early 1960s, the sources looked, through the telescopes of the time, almost exactly like ordinary stars. Small, sharp, unresolved points of light, nothing like the soft, extended glow of a galaxy. But their radio emission and their spectra behaved nothing like any star anyone had ever catalogued. Astronomers needed a name for something that looked stellar without actually being a star. The term they settled on, quasi-stellar radio source, eventually contracted into the word used ever since, quasar. Built directly into the object's own name is an admission that early observers weren't entirely sure what they were looking at, only that it resembled something it clearly wasn't. That's the exact trap TON 618 fell into 13 years before the word even existed. A survey looking for faint blue stars found something that looked, through a 1950s telescope, exactly like the thing it was searching for. The failure wasn't a lack of care, it was a category the astronomers of 1957 had no name for yet, encountered by instruments built to recognize something else entirely. TON 618 is extreme, but it is not alone in its category. And understanding where it sits among its own relatives sharpens exactly what makes it stand out. Since Martin Schmidt's 1963 identification of 3C 273, astronomers have catalogued many thousands of quasars, scattered across the observable universe, the vast majority of them considerably fainter and considerably less massive than TON 618. Quasars, as a category, span an enormous range. Some barely outshine their host galaxy at all, while a smaller, rarer group, astronomers call them hyperluminous quasars, cross a luminosity threshold so extreme that they rank among the brightest single objects the universe has ever produced. TON 618 sits firmly inside that rarer group, one of a comparatively short list of quasars bright enough and massive enough to earn the label. Astronomers draw the line for hyperluminous at an extraordinarily high luminosity threshold, reserved for only the most extreme quasars known, and TON 618's estimated output clears that bar comfortably, sitting among a genuinely small handful of objects extreme enough to earn the classification at all, rather than the merely luminous or very luminous tiers most active quasars fall into instead. What makes TON 618 unusual, even within that already rare company, isn't simply the number attached to its mass. It's the combination: a hyperluminous quasar, radio loud, sitting at a redshift extreme enough to place it within the universe's first 3 billion years, discovered by accident decades before anyone had the tools or the concept to recognize what they'd found. Plenty of other quasars share one or two of those properties. Very few share all of them stacked together in an object that first entered the scientific record as an entry in a catalogue of dying stars. If you wanted to find TON 618 with your own eyes, on a clear night, no telescope in a typical household would get you there. It's worth understanding exactly why. Because the reason says something honest about how faint one of the brightest objects in the universe can still look from far enough away. TON 618 sits within the constellation Canes Venatici, a faint, unassuming pattern near the handle of the Big Dipper, itself made up of only two modest stars, and rarely noticed by anyone who isn't specifically looking for it. Somewhere within that quiet patch of sky sits a point of light with an apparent magnitude of roughly 15.9, a measure of how bright an object looks from Earth, where lower numbers mean brighter, and where the faintest stars visible to an unaided human eye on a dark night sit only around magnitude 6. TON 618, at nearly 16, is thousands of times fainter than the dimmest star most people have ever consciously noticed, invisible not just to the naked eye, but to the modest backyard telescopes most amateur astronomers own. That's the strange arithmetic sitting underneath this entire story. An object luminous enough that its own light alone could sterilize a planet at close range looks, from 10.8 billion light-years away, like nothing at all, fainter than thousands of ordinary, nearby, thoroughly unremarkable stars scattered across the same patch of sky. Brightness, out here, was never really about how much light something makes. It's about how much of that light survives the trip. There's a second layer of illusion sitting on top of the first, and it applies to every constellation ever drawn. Not just this one. Canes Venatici, like every constellation, is a human pattern, not a physical grouping. Its two named stars happen to sit at wildly different distances from Earth and from each other, sharing nothing but a coincidental line of sight that made sense to draw a shape around. Ton 618 doesn't belong to that constellation in any physical sense either. It simply happens to sit, by pure chance of geometry, behind the same small patch of sky, at a distance so much greater than either of Canes Venatici's own stars that comparing them is closer to comparing a lamp on a nearby table to a lighthouse on a coast nobody in the room has ever visited. The stars forming the shape are neighbours, relatively speaking. Ton 618 is simply passing through the same window, from a distance neither of them shares. Ton 618 carries one more label worth understanding before this goes any further. Astronomers classify it as radio loud, the same property that first betrayed it back in 1970. Only a minority of quasars, commonly estimated at somewhere around 1 in 10, earn that label at all. Most shine brilliantly across visible and ultraviolet light without ever producing the kind of strong radio emission that first gave Ton 618 away. Whatever internal condition separates a radio-loud quasar from a radio-quiet one remains an active area of research in its own right. But Ton 618, whatever the cause, belongs to the noisier, rarer minority. Radio-loud quasars, unlike their quieter cousins, launch narrow jets of charged particles outward from the immediate neighborhood of the black hole, accelerated to velocities close to the speed of light by magnetic fields twisted taut around the spinning disk. A jet like that doesn't behave like an explosion. It behaves more like a hose left running for millions of years, pushing a thin, focused stream of particles outward along the black hole's spin axis, far beyond the accretion disk, far beyond the galaxy itself, out into whatever gas happens to be waiting in the space around it. The mechanism that launches it is still debated in its finer details. The broad picture is well established. A spinning black hole, threaded by magnetic field lines dragged along by the swirling disk, can act like a kind of natural particle accelerator, flinging matter outward at speeds close enough to light that the jet barely spreads at all over distances of hundreds of thousands of light-years. Spin turns out to matter enormously here, in a way that's easy to miss. Astronomers generally suspect that the strongest, most persistent jets favor black holes spinning rapidly on their own axis. The faster the spin, the more efficiently the surrounding magnetic fields seem able to siphon rotational energy outward into a jet, a black hole that formed quickly or merged violently with others earlier in its history, tends to spin faster than one that grew slowly and quietly. Ton 618's status as radio loud may itself be a clue about its own past, hinting at a black hole that arrived at its current, disputed mass through something more violent than a slow, steady accumulation of gas. Whether that stream points anywhere near Earth is mostly luck of geometry, and in Ton 618's case, that same jet turns out to matter for a discovery that came decades after Ulrich's first spectrum, one that has nothing to do with the black hole's mass, and everything to do with what its mass has been doing to the space around it. It's worth pausing to place Ton 618 next to the black hole closest to home, if only to notice how differently the same basic machine can behave depending on how much it currently has to eat. Sagittarius A, at the center of our own galaxy, is not a quasar. It has no accretion disk blazing with the light of 140 trillion suns, no jet stretching hundreds of thousands of light years outward, nothing resembling TON 618's furious activity. Starved of a steady supply of infalling gas, it sits in what astronomers call a quiescent state, occasionally flickering with faint flares as small clumps of gas or dust wander close enough to be consumed, but otherwise close to silent by comparison. And yet many astronomers suspect that even our own galaxy's black hole passed through a much more active, quasar-like phase earlier in cosmic history, back when the Milky Way had more loose gas available nearby to feed it, before billions of years of quiet accretion gradually exhausted the easy supply. A quasar, in other words, isn't a permanently different category of black hole. It may simply be what any sufficiently massive black hole looks like while it's still being fed at a furious rate. A phase, not a species. TON 618, by that light, might not be an alien kind of monster at all. It might be showing what our own currently quiet galactic center looked like, or something close to it, in a much younger and hungrier universe. Before any of tonight's numbers could exist, the idea of a black hole itself had to survive decades of its own. Scientists doubting it, which is worth remembering every time a number this extreme starts to feel unquestionable. The mathematics describing an object like TON 618's black hole traces back to 1916, when Carl Schwarzschild, working out solutions to Einstein's newly published equations of general relativity while serving on the German front during the First World War, found a solution describing a point so dense that not even light could escape its gravity. Schwarzschild mailed his solution to Einstein from the trenches and died within the year of a disease contracted during his service, never living to see the idea taken seriously, debated, or eventually confirmed. Einstein himself, for years afterward, treated the result as a mathematical curiosity rather than a description of anything that could physically exist. A strange edge case the equations technically allowed, not a prediction he expected nature to actually build. Decades later, in 1967, the physicist John Wheeler popularized the term black hole. At long last, a name ordinary people could use. A similar dismissal happened again in the 1930s, when a young astrophysicist named Subramanian Chandrasekhar calculated that a dying star beyond a certain mass couldn't settle into a stable white dwarf at all. It would have to keep collapsing, with nothing left to stop it. Arthur Eddington, one of the most respected astronomers alive at the time, publicly ridiculed the calculation in front of the Royal Astronomical Society, dismissing the very idea that nature would allow such an outcome. Chandrasekhar was right. It took decades, and eventually a Nobel Prize awarded in 1983 for the field to fully agree with the young astrophysicist over the famous one who'd mocked him. It took until the final decades of the 20th century for indirect evidence. Stars orbiting something unseen at the center of our own galaxy, X-rays flaring from matter being torn apart around invisible companions, to convince most of the field that these objects weren't just solutions on a page. Direct evidence, the kind that finally silenced most remaining doubt, arrived only in 2015, when gravitational waves from two colliding black holes were detected for the first time, nearly a century after Schwarzschild first wrote down the equation predicting they could exist at all. Every number in tonight's story about TON 618 rests on that century of accumulated confidence. And the same field that took 50 years to fully believe black holes were real at all is the same field currently unable to agree, after 15 years of trying, on how much just one of them actually weighs. Both facts belong to the same discipline, practiced with the same care, arriving at very different levels of certainty depending on exactly what's being asked. Pause on the word itself for a moment, because biggest black hole has been carrying more assumptions than its two syllables let on. Biggest could mean most massive, which is the meaning this entire investigation has mostly been chasing. It could just as easily mean largest event horizon, which usually tracks mass closely but not perfectly, depending on a black hole's spin. It could mean brightest, in which case the accretion disk's luminosity, not the black hole's mass at all, becomes the relevant number, and TON 618 competes on entirely different terms. It could even mean most massive relative to its host galaxy, a ratio some astronomers consider more scientifically meaningful than raw mass alone, since it says something about how a black hole and its galaxy grew together rather than simply how heavy one particular object happens to be. Every one of those readings is defensible. None of them is obviously the correct one, and popular science rarely specifies which meaning it's actually using before reaching for the word biggest and moving on. TON 618's own reputation was built on the simplest, least qualified version of the claim. Heaviest, full stop. Precisely because that version required the least explanation to repeat. The more careful versions of the question, the ones this investigation has spent 2 hours sitting inside, all turn out to be considerably harder to answer, with a single confident word. Before reaching that discovery, the mass question deserves one more complication, because 66 billion or 40.7 billion was never really competing against each other for the title of biggest black hole known. It was competing, the whole time, against a third number entirely, sitting quietly in a completely different galaxy, measured by a completely different method, and rarely mentioned in the same breath as TON 618 at all. A galaxy cluster is not a single galaxy. It's hundreds or thousands of galaxies, bound together by their mutual gravity, along with a vast reservoir of superheated gas filling the space between them. At the center of nearly every one sits a single dominant galaxy, usually the largest and oldest in the cluster, anchoring the whole structure. The Phoenix Cluster's central galaxy is exactly that kind of anchor. And at its center sits a black hole current estimates place at around 100 billion solar masses, heavier than either of TON 618's contested figures, and heavier by a comfortable margin even against the higher of the two. That number didn't come from a redshifted emission line at all. The Phoenix Cluster's black hole sits close enough, and its surrounding stars and gas are resolved clearly enough that astronomers can measure its mass by watching how stars and gas actually move under its gravity across the galaxy's core, a dynamical measurement built from motion that can be mapped directly, rather than inferred from the width of one smeared spectral line in the unresolved light of an object 10 billion light-years away. The Phoenix Cluster itself earned its own reputation for extremes before its black hole ever entered this conversation. Its central galaxy sits inside one of the most powerful cooling flows ever measured, a vast reservoir of hot cluster gas steadily cooling and raining down onto the galaxy's core, feeding one of the highest rates of new star formation ever recorded in a cluster environment, hundreds of new stars worth of material condensing out of that inflow every year. A black hole that massive, sitting at the base of a cooling flow that dramatic, wasn't a quiet coincidence either. Astronomers studying the cluster generally treat the two extremes, the record-setting star formation and the record-contending black hole, as very likely connected chapters of the same unusually active system. If biggest black hole ever found is the claim doing the scaring, that claim may not belong to TON 618 at all. It likely hasn't for as long as the Phoenix Cluster's number has been on the table. The reputation outlived the ranking. Popular science kept repeating 66 billion, the biggest black hole ever measured, well past the point where a heavier, more reliably measured black hole existed in the literature under a different name that never made it onto the same lists. Partly because TON 618 already had a story attached to it, a misidentified star, a decades-old catalogue number, a redshift that made headlines in its own right, and a number heavy enough to feel definitive. The black hole in the Phoenix Cluster never got the same introduction. One of the more scientifically meaningful versions of biggest, mentioned a moment ago, is a black hole's mass measured against its own host galaxy, a ratio astronomers use in better studied systems to understand how tightly a black hole's growth and a galaxy's growth stay linked over billions of years. It's worth being honest about why that comparison simply cannot be made for TON 618 at all. Calculating that ratio requires knowing the host galaxy's own mass, typically measured from its total starlight or the motion of its stars. Exactly the measurement TON 618's own glare makes impossible. The galaxy is there, presumably built from ordinary stars the same way every other quasar's host galaxy is. It has simply never been weighed, because it has never been seen well enough to weigh. Whatever ratio actually holds between TON 618's black hole and its own galaxy remains, for now, entirely unknown. Not a small number, not a large one, simply an absent one, waiting on an observation nobody currently knows how to make. That absence matters more than it might first appear. Some of the most interesting open questions about supermassive black holes involve objects whose mass, relative to their galaxy, breaks the pattern seen almost everywhere else. Galaxies with black holes that seem disproportionately heavy for how small or faint the surrounding galaxy is. TON 618 might be an entirely ordinary example of that established relationship. It might be a dramatic outlier. A black hole that outgrew its own galaxy by a wide margin. Nobody currently knows which. And the glare that made this entire investigation necessary is the same glare preventing that particular question from ever being answered with current instruments. The reason this isn't a simple case of one paper beating another comes down to how differently the two masses were built in the first place. A dynamical mass, like the Phoenix clusters, comes from watching real, resolved motion. Stars and gas clouds tracked individually, their velocities measured directly. No assumptions needed about the geometry of an accretion disk billions of light years away. It's the same style of measurement, in spirit, as tracking a planet's orbit around the sun. Patient, direct, and about as trustworthy as astronomy gets. A virial mass, like both of TON 618's competing figures, starts from something far less direct. The width of a single emission line in the combined light of an entire accretion disk. An object too small and too distant to resolve into individual moving parts at all. Every step from that line width to an actual mass depends on assumptions. About the disk's geometry, about how closely a given spectral line traces the gas actually orbiting the black hole, about calibrations built from nearer, better understood systems, and then extrapolated outward to objects 10 billion light-years past, where anyone can double-check the extrapolation directly. Neither method is fake science. Both are the best tool available for the object in front of them. Dynamical measurements simply aren't possible for something as distant and unresolved as TON 618. Virial measurements aren't necessary for something as close and well-mapped as the Phoenix cluster's core, but it does mean that ranking black holes by mass across both methods at once is a little like ranking runners by combining stopwatch times with estimates based on how out of breath they looked at the finish line. The numbers can both be honest and still not be measuring quite the same thing. This is, in a smaller way, the same problem that separates Schemmer's number from Gay's. Every mass on every biggest black hole list carries an invisible footnote listing exactly which method produced it, and that footnote rarely survives the trip into a headline. A ranking assembled from footnote-free numbers isn't really a ranking of black holes. It's a ranking of how confidently each number got repeated before anyone checked what was actually behind it. There's a third way astronomers weigh black holes closer to home. It's worth naming precisely because it explains why nobody has simply used it on TON 618 instead of arguing over spectral lines. In relatively nearby, well-studied galaxies, astronomers have found a strikingly tight relationship between a black hole's mass and an entirely different property of its host galaxy. The average speed at which stars orbit and jostle around the galaxy's center, called the velocity dispersion. Heavier central black holes reliably sit inside galaxies where that stellar motion runs faster. a pattern astronomers call the M-sigma relation, tight and consistent enough across dozens of nearby galaxies to function as its own kind of mass estimator, entirely independent of anything happening in a quasar's accretion disk. That relationship simply cannot be applied to TON 618. Measuring the motion of individual stars requires resolving a galaxy into countless separate points of light, tracking their velocities one by one, a task that demands relatively well-resolved galaxies. TON 618's own host galaxy, remember, is not resolved at all. It's invisible, buried entirely behind the quasar's glare. The M-sigma relation, for all its usefulness elsewhere in astronomy, simply has no galaxy to work with here. Virial mass, built from the width of a single emission line, isn't the method astronomers prefer for an object like TON 618. It's the only method left once every better option has been ruled out by distance alone. It would be easy, at this point, to treat the gap between 66 billion and 40.7 billion as a narrow argument between two research teams. Interesting mostly as trivia, it's worth pausing to say plainly why astronomers actually care. Individual black hole masses like TON 618's feed into a much larger project, mapping how black holes and galaxies grew up together across cosmic history, a relationship astronomers increasingly believe runs in both directions, each shaping the other's growth over billions of years. Get enough individual masses right, across enough objects at enough different redshifts, and a population-wide pattern emerges. A black hole mass function, tracking how common black holes of different sizes were at different points in the universe's history, which in turn tests entire theories about how galaxies assemble, how quasars regulate their own fuel supply, and how much influence a single black hole's feedback can have on the fate of everything orbiting it. A single mass estimate swinging by nearly a factor of 2 doesn't just change one number in one table. It shifts where TON 618 sits in that larger population picture, changes how unusual an object of its kind actually was for its era, and adjusts, even if only slightly, the broader story astronomers are trying to build about how the universe's most extreme structures came to exist at all. That's the quieter, less dramatic reason this disagreement never got fully resolved by simply picking a number and moving on. The number was never just about TON 618. It's a data point inside a much larger argument that's still being built. One contested measurement at a time. Whichever number you trust, 66 billion, 40.7 billion, or the Phoenix Cluster's 100 billion in some other galaxy entirely. The distance involved has already stopped behaving like anything a body has evolved to judge. It's worth pausing here. Not to add another number, but to ask what any of this would actually feel like, because the honest answer runs backward from what most people expect. Fall toward a black hole built from an ordinary dying star, the kind that leaves behind 10 or 20 solar masses. The outcome is brutal long before you reach the horizon. Gravity pulls harder on whatever part of you is closer to the black hole than on whatever part is farther away, and around a small black hole, that difference, the tidal force, grows savage within a distance, still comfortably outside the event horizon. Feet first, you'd feel your legs stretched harder than your head, then your body drawn out thinner and thinner. The process astronomers call spaghettification finished well before you ever crossed the boundary of no return. The horizon of a stellar mass black hole is not a place anything living ever reaches intact. Around something the size of TON 618's black hole, the physics runs almost exactly backward. Tidal force depends on how sharply gravity changes over a given distance, and a horizon this enormous, spanning 1,300 astronomical units, or 800, depending on which measurement you trust, means gravity barely changes at all across the length of an ordinary human body. Even right at the boundary itself, you could, in principle, cross the event horizon of TON 618, feeling nothing unusual whatsoever. No stretching, no crushing, No signpost of any kind marking the exact moment the universe stopped letting you leave. The wall isn't a wall at all at that scale. It's a threshold you could drift through in your sleep, discovering only afterward, and only by trying to leave, that you no longer can. That gentleness has a limit, and the limit matters just as much as the crossing does. General relativity doesn't stop applying once you're inside. It simply stops being escapable. Deeper inside a black hole this size, the same tidal stretching that destroys a body instantly outside a small black hole still happens eventually. The equations that describe the interior all point toward a singularity, a place where the mathematics of general relativity stops making reliable predictions at all, the same kind of breakdown that shows up at the very beginning of the universe itself. The difference TON 618 size buys you isn't survival, it's distance. A horizon so large that the gentle part of the fall, the part with no warning, no violence, nothing to signal that anything has changed, can last for what would feel, from the inside, like a very long, very quiet while before the equations catch up with you. Whichever version sounds more frightening is a personal question, not a scientific one. But it's worth admitting that the gentler version, silent, undetectable in the moment of crossing, unsettles in a way the violent one doesn't quite manage. A monster that rips you apart on the way in is, in its own brutal way, honest about what it is. A monster this size doesn't announce itself at all. It simply stops answering. At some point, when you try to turn around, none of the last few minutes describe what TON 618 would actually look like, because falling toward it is not a vantage point anyone survives to report back from. Imagine, instead, a safer version of the same scene, a hypothetical observation post, shielded from every form of radiation that would otherwise end things instantly, parked at a comfortable distance, not to test the physics of falling in, but simply to look. There would be no black circle waiting politely in the middle of empty space, the way illustrations sometimes suggest. The accretion disk would dominate everything. A churning, layered ring of light-year-wide gas glowing across a spectrum far wider than anything a human eye alone could register. Fierce blue-white near its innermost edge, where the gas moves fastest and burns hottest, fading through fainter colours further out, where the material has not yet been dragged into the final, violent stretch of its fall. The black hole itself would appear only as an absence at the centre of all that light, a dark, perfectly still core, warping the glow around its edges into a faint, curved halo, the way a heavy object dimples a stretched sheet. Except here, the sheet is space itself, and the dimple has no bottom anyone has ever measured. Looking straight along the axis of the jet, if geometry happened to allow it, would reveal a second sight entirely, a narrow column of matter moving close enough to light speed that the ordinary rules of brightness stop applying evenly in every direction, beamed outward for a distance longer than most galaxies are wide, fading slowly as it thinned into the cloud of gas discovered decades later, still visibly bending and rippling wherever it met resistance. None of this would arrive with sound. Space carries no sound at all, and even the most violent event imaginable produces nothing a human ear, or any ear, could register from a safe distance. What would arrive is heat and light in quantities the body has no framework for, and, at exactly the right angle, the quiet, motionless suggestion of a boundary sitting at the center of it all, doing nothing dramatic whatsoever, simply refusing, patiently, to let anything that crossed it return. The innermost edge of the disk, closest to the black hole and moving fastest, would radiate mostly in ultraviolet and even X-ray wavelengths, invisible to human eyes without instruments to translate them into visible color, which is part of why illustrations of quasars always involve some artistic choice about what to actually show. The visible light humans could register directly would come mostly from the cooler, outer reaches of the disk, a comparatively gentle blue-white glow sitting atop a furnace whose truly violent output would remain, to unaided eyes, entirely invisible. This scene is not a measurement. Nobody has stood at that safe distance, and nobody ever will. It's offered here as a way of holding the numbers already covered: the disk, the jet, the horizon. Inside a single mental image, built from physics that is well understood even though the vantage point imagining it is entirely invented. One more piece of the gentleness described a moment ago deserves its own attention, because it sounds at first like it can't possibly be true. At TON 618 scale, the black hole is, on average, less dense than the air currently filling whatever room this is being heard in. An event horizon's radius grows in direct proportion to its mass, double the mass. And the horizon's radius doubles too. Volume, though, grows with the cube of that radius, which means a black hole's average density, mass, divided by the volume enclosed within its horizon, actually falls as the black hole gets more massive, not rises the way intuition usually expects density to behave. A stellar mass black hole is almost unimaginably dense, packing a few times the sun's mass into a sphere only a few kilometers across. Scale the same physics up to 66 billion solar masses. The density spread across that much larger volume works out to something under 1/100th the density of ordinary air. None of that makes crossing the horizon any safer, and it doesn't change anything about the singularity waiting deeper inside. It simply means density was never actually a meaningful description of what makes a black hole dangerous. What matters is the total mass, concentrated anywhere within the horizon, not how tightly packed that mass happens to be at the boundary itself. Which is exactly why a horizon this enormous can be this gentle to cross and this impossible to leave at the very same time. For decades, the entire story of TON 618 was a story about one point in space and how much it weighed. In 2021, that story got a great deal larger, and the black hole itself had almost nothing to do with the change. A single dish, however large, couldn't have found this structure. The Atacama Large Millimeter Array works the way the Event Horizon Telescope does, just at a different scale. Dozens of individual radio dishes, spread across a high desert plateau in northern Chile more than 5 kilometers above sea level, combining their signals electronically so precisely that together they behave like one much larger telescope capable of resolving faint, extended structures no single instrument could gather enough light to detect on its own. Using that combined array, astronomers mapped the region of sky around TON 618 and found something no single emission line could have revealed, glowing faintly in a specific ultraviolet transition called Lyman alpha, surrounding the quasar on a scale that dwarfed the black hole's own neighborhood entirely. Structures like this, astronomers call them Lyman alpha blobs, turn up elsewhere in the distant universe too, usually near unusually active galaxies, but rarely on a scale this large, and rarely this cleanly aligned with anything as specific as a single jet. The structure around TON 618 showed at least two major components, each one estimated to hold something in the neighborhood of 50 billion solar masses of gas. Not the black hole's mass, but the raw material drifting in the space around it, cold and largely untouched by the furnace at the center. One component traced an outflow closer to the quasar itself, gas actively being pushed outward by the disk's radiation and the jet's momentum. The other traced a far larger, more diffuse reservoir sitting in what astronomers call the circumgalactic medium, the loose, thin gas that surrounds a galaxy well beyond its visible edge, neither fully part of the galaxy nor fully free of it, and the whole structure lined up, almost exactly, with the direction of TON 618's radio jet, the same narrow stream of particles first hinted at by that 1970 Bologna survey, still running outward, still finding gas to push against, more than half a century after anyone first noticed this object was shouting in radio waves. An alignment that precise, across a structure that large is not the kind of thing that happens by coincidence between two unrelated pieces of a galaxy. Something about the quasar's own activity appears to be organizing gas on a scale the black hole's own gravity could never reach directly. It helps to slow down on that gas figure for a moment, because 50 billion solar masses of gas risk sliding past as just another large number in a story already full of them. The gas ALMA detected isn't glowing because it's hot. It's cold. By astronomical standards. Thin, largely molecular hydrogen, the same basic raw material every star that has ever ignited was originally built from, sitting at temperatures far below anything found near the blazing accretion disk at the system's center. 50 billion solar masses of that material, in the right conditions, is enough raw ingredient to build tens of billions of ordinary stars, an entire additional galaxy's worth of potential sitting quietly in the space around Ton 618, currently doing nothing more dramatic than drifting, slowly, in whatever direction the quasar's jet and gravity are currently pushing it. Whether that gas eventually collapses into new stars, gets blown away entirely by the quasar's own violence, or simply drifts for billions of years without doing much of anything, is exactly the kind of open question this discovery raised rather than closed. Astronomers studying similar large-scale gas structures around other active galaxies have found examples of both outcomes elsewhere in the universe, some triggering bursts of new star formation, others getting stripped away and dispersed before they ever get the chance. Ton 618's own cloud hasn't been definitively assigned to either category yet. It is simply out there, cold, immense, and quietly waiting, whichever way its actual fate eventually breaks. Measure the whole gas structure from edge to edge, and the number stretches past 100 kiloparsecs. A parsec being roughly 3¼ light years, a kiloparsec, 1,000 of those, the unit astronomers usually reach for once light years alone start feeling too small to be convenient. More than 330,000 light years across. Our own Milky Way, from one edge of its stellar disk to the other, spans somewhere close to 100,000 light years. The cloud surrounding Ton 618 is not merely large, it's roughly 3 Milky Ways wide, built almost entirely from gas, wrapped around a single point of light that itself would still fit comfortably inside the width of one ordinary solar system. Picture the proportions honestly, because they resist a first attempt at intuition. If Ton 618's accretion disk, the 1 light-year wide furnace producing all the light this entire investigation has been built on, were shrunk to the size of a single grain of sand, the surrounding gas cloud, at the same scale, would sprawl out to roughly the size of a small city block, a grain of sand, generating enough light to be seen across 10 billion years, sitting at the center of a haze wide enough to swallow a neighborhood. This changes what the monster should even mean. Once you sit with it, Ton 618 was never just a black hole with a number attached. It's a black hole, an accretion disk a light year across, a jet running outward for who knows how long, and a cloud of cold gas larger than several galaxies stacked together, aligned with that same jet, as if the black hole's activity has been quietly rearranging its surroundings on a scale that has nothing to do with its own event horizon. Astronomers studying quasars like this one increasingly suspect that structures this size, this aligned, aren't coincidence, that an object powerful enough to outshine its own galaxy might also be powerful enough to shape the gas across hundreds of thousands of light years around it, feeding future generations of stars, or starving them, depending on exactly how that jet and that gas interact over cosmic time. A galaxy's entire future, how many more stars it ever gets to build, may already be getting decided by a jet most of that galaxy's own stars will never live to see arrive. Nobody has finished answering that question. It's mentioned here not because it's settled, but because it's the kind of complication a genuine investigation runs into and has to sit with honestly. Every time this story seems to have settled on a top scale, a new instrument finds a way to make the scale larger again. Suppose, for a moment, purely as an exercise and not as anything astronomers claim to know, that an ordinary planet existed somewhere in Ton 618's hidden host galaxy, orbiting some ordinary star at a safe distance from the quasar itself. What would its sky actually look like? Nothing about such a planet's days and nights would resemble Earth's. A quasar this luminous would flood the entire galaxy with light, far brighter than anything a single star nearby could compete with. Day or night, drowning out the ordinary pattern of light and dark a rotating planet usually experiences. Depending on exactly how far from the center such a world sat, its sky might never truly darken at all. A permanent, directionless glow instead of stars, the galaxy's own core outshining every constellation its inhabitants might otherwise have drawn. This is offered only as an imagined scene, not a claim about any real planet, because no such planet has ever been detected, and Ton 618's host galaxy remains entirely unstudied behind the quasar's own glare. It's a useful way to hold the luminosity numbers already covered. Translated into the one setting, this entire channel usually cares about most: what a sky and a night would actually feel like from underneath it. There's a second complication, and it has nothing to do with size at all. It has to do with when. Remember the number from the very beginning of tonight, a redshift of 2.219, meaning the light now reaching Earth left Ton 618 when the universe itself was less than 3 billion years old, a little over a fifth of its current age. That timing matters more than it sounds like it should, because building a black hole this large, by any of the standard, well-understood processes astronomers rely on elsewhere, takes time. Ordinary stellar remnant black holes start small, tens of solar masses at most, left behind when a massive star runs out of fuel and collapses under its own weight. From there, they grow by slowly pulling in surrounding gas at rates physics itself puts a rough ceiling on, a limit called the Eddington rate, past which the radiation pressure from all that infalling, superheated material should start pushing new material away rather than letting it fall further in. It's a kind of natural speed limit built into the physics of light pressure itself. Accrete too fast, and the black hole's own glow starts fighting off its own food supply. Run the arithmetic on ordinary growth, starting from an ordinary seed, accreting at the ordinary limit, getting to tens of billions of solar masses within the first 3 billion years of cosmic history is, at best, uncomfortably tight. Even granting a black hole a generous head start and letting it accrete at the maximum allowed rate, without interruption for that entire span, most standard models struggle to close the remaining distance to numbers like 40 billion or 66 billion solar masses. Ton 618 is far from alone in this problem. Astronomers have found a small, growing family of quasars from this same early era, scattered across different surveys and different research teams that all share the same uncomfortable arithmetic. Objects that look, on paper, too heavy for the amount of time the universe had actually given them to build something that size. The record for earliest known oversized black hole currently belongs to an object called ULAS J 1120 plus 0641, a quasar discovered in 2011, sitting at a redshift of 7.085, meaning its light left home less than 770 million years after the Big Bang, barely a 20th of the universe's current age. Its black hole weighs a comparatively modest 2 billion solar masses, tiny next to either of Ton 618's disputed figures. Even that modest number is difficult to explain given how little time the universe had offered it to grow. Ton 618, arriving later in cosmic history at a more generous 3 billion years, actually has more time to explain than ULAS J 1120 plus 0641 does. And still, by most standard growth models, not quite enough. Finding those objects at all is its own kind of ongoing search. Wide-field sky surveys, scanning enormous swaths of sky and sorting candidate objects by color and brightness, rather than examining each one individually, flag possible distant quasars first. Only afterward does a dedicated spectrograph confirm whether a given candidate's redshift is real and how extreme it actually is. Most candidates turn out to be closer, more ordinary objects wearing a misleading color. A small number, each time, turn out to be genuine, extraordinarily distant quasars. A slow, patient filtering process not entirely unlike the one that eventually separated TON 618 from every other faint blue dot in the Ton and Sintler catalogue, just conducted deliberately now instead of by accident. Two broad families of explanation currently get taken seriously for how this happens, and neither one has fully closed the case. The first proposes that some early black holes never started small at all. Instead of forming from the collapse of a single dying star, a small number of unusually massive, unusually cold clouds of primordial gas may have collapsed directly into black holes, weighing tens of thousands of solar masses right from birth. No stellar stage in between, no slow accumulation from a stellar-sized seed. The conditions required are specific and rare. A cloud large enough, and crucially cold and calm enough, to avoid fragmenting into ordinary stars, the way gas clouds almost always do, collapsing instead as one single, coherent mass. Give a seed like that a significant head start. The remaining growth needed to reach tens of billions of solar masses within 3 billion years becomes far more plausible under ordinary accretion rates. The second proposes that the Eddington limit itself isn't as strict a ceiling as it looks on paper, that under the right, messy, short-lived conditions, a young black hole might accrete gas faster than the textbook limit allows, in bursts too brief and too chaotic for the outward radiation pressure to fully choke off the inflow before it's already happened. Some models suggest this kind of super Eddington feeding could happen when in falling, gas is unusually thick or clumpy, briefly trapping its own outward-pushing radiation before that radiation manages to escape and do its usual job of holding new material back. A black hole that occasionally cheats its own speed limit for a few tens of millions of years, here and there, could plausibly close much of the remaining gap without needing an unusually large starting seed at all. Neither explanation has won. Both remain live possibilities in the astrophysics of the early universe. And TON 618, sitting exactly in the era where this problem gets sharpest, doesn't resolve which one is correct. It's entirely possible both mechanisms played some role, in some order, in some combination current models haven't fully worked out. It just makes clear that whichever mass number eventually wins the argument, 66 billion, 40.7 billion, or something revised again by an instrument that doesn't exist yet. The timing problem sitting underneath that number isn't going away on its own. TON 618 sat misidentified for 13 years, inside a catalogue built and checked by careful astronomers, simply because the right instrument hadn't yet been pointed at the right coordinates. It's worth asking, honestly, how unusual that actually was. 20th century sky surveys like Tonant Sintler's produced enormous catalogues filled with hundreds of thousands of objects, sorted using whatever instruments and whatever categories existed at the time each survey was made. Every one of those catalogues necessarily reflects the limits of its own era. Objects get sorted into the boxes available when the sorting happens, and boxes that don't exist yet. Quasar in 1957. Or, potentially, some category not yet named in any catalogue being compiled today simply aren't available to file anything into. Astronomers who study these older archives have, in fact, gone back and found other overlooked quasars and unusual objects hiding in exactly this way, misfiled decades earlier, under mundane labels, waiting for someone with a newer instrument, or simply a newer question to look again. Nobody can say with any precision how many other TON 618 seconds might still be sitting quietly in old catalogues, correctly photographed and completely misunderstood, waiting for their own version of a 1970 radio survey? That uncertainty isn't a flaw in the historical record. It's simply what it means for a species to keep building better instruments than it had the decade before. Every finished catalogue is also, unavoidably, a list of everything that particular generation of tools wasn't yet capable of recognizing. There's a useful distinction, borrowed loosely from how investigators of any kind actually work, that clarifies exactly what kind of evidence this entire hour has been built from. A signature can convict without anyone ever seeing the hand that wrote it. It carries enough distinctive information, pressure, slant, the particular way a specific letter loops, to identify its source reliably, entirely without a photograph, a fingerprint, or a face. Spectroscopy works on precisely that principle, translated into light. A spectral line's exact wavelength, width, and shape carry a signature specific enough to reveal composition, motion, temperature, and, with enough care, even the mass required to explain what's producing it without ever needing to resolve the source into an actual picture. Every fact gathered about TON 618 tonight is a signature, not a face. The redshift is a signature. The mass estimates are signatures, read off two different lines with two different handwriting quirks that don't quite agree. The jet, the disk, the surrounding cloud of gas. Every one of them was identified the same way, through evidence specific enough to trust without ever amounting to a photograph. That's not a weaker form of knowledge than an image would provide. It's simply a different one, built on inference carried out with genuine rigor rather than a picture anyone could simply glance at and confirm by eye. At some point in an investigation like this, it would help enormously to just look at the thing directly. That option has never been available for TON 618, and understanding why sharpens exactly what the scariest black hole is actually claiming. In 2019, the Event Horizon Telescope produced the first true image of a black hole's shadow. The supermassive object at the center of the galaxy, M87, roughly 6.5 billion solar masses, captured as a dark circle ringed by glowing gas. 3 years later, the same collaboration imaged Sagittarius A, the comparatively modest black hole, a little over 4 million solar masses, anchoring the center of our own Milky Way. Neither image came from a single telescope. Both were assembled from a technique called very long baseline interferometry, linking radio dishes on opposite sides of the planet together so precisely that, in effect, they behave like one single telescope the size of Earth itself. The only way to resolve an object as small on the sky as a black hole's shadow. Both images exist because both objects are, relatively speaking, close. M87 sits around 53 million light-years away, and our own galactic center a mere 26,000. Close enough, combined with each object's genuine size, for an Earth-sized virtual telescope to resolve an angle small enough to count as an image at all. And even then, both projects took years of coordinated observation, data too large to transmit over the internet, and shipped instead on physical hard drives, before a single picture emerged. TON 618 fails that test by an overwhelming margin. Even granting it the larger of its two disputed masses, it sits roughly 200 times farther away than M87 in an era of the universe far too distant and far too faint for any existing or currently planned instrument to resolve its shadow the way the Event Horizon Telescope resolved M87's. Distance shrinks an object's apparent size on the sky in a way that raw physical size can't fully make up for, no matter how enormous the object actually is. As of the writing of this video, no image of TON 618 exists, and none has been attempted, because none is currently possible. Every fact in this entire hour, the mass, the redshift, the jet, the cloud of gas 3 Milky Ways wide, was reconstructed entirely from spectroscopy. Light, split into wavelengths, analyzed for what it implies, never once resolved into a picture of the thing producing it. That's worth holding on to as its own kind of answer. TON 618 has never been seen. It has only ever been inferred. Read like a signature, off light, that left its source before there was anyone anywhere to read it. Nothing currently on any telescope's drawing board changes that. Future infrared spectrographs, built for the next generation of extremely large ground-based telescopes, may eventually pin down hydrogen beta at TON 618's redshift more cleanly than anything available to Schemmer's team in 2004. That alone could finally settle the gap between 66 billion and 40.7 billion. An image, though, is a different kind of problem entirely. One that distance solves for no instrument currently funded, planned, or seriously proposed. Whatever gets resolved about TON 618 inches the coming decades, it will almost certainly still arrive the same way everything in this story already has. As a number extracted from a line in a spectrum, not a shape resolved in a picture. TON 618 is not the first object to wear the label biggest black hole ever found. An understanding that history puts its current, contested standing in a gentler light. Before TON 618's mass was ever calculated, other black holes briefly held the same reputation, only to be displaced as better instruments and better methods came online. A pattern that has repeated, quietly, for as long as astronomers have been attempting these measurements at all. Each new record holder tends to arrive the same way. One team, one method, one striking number, widely reported, until a later team, working with a different instrument or a more careful technique, either confirms it, revises it, or hands the title to something else entirely. The record has never once been settled permanently. It has only ever been the current best guess, held by whichever object happened to be measured most recently, by whoever happened to be looking. Seen against that pattern, TON 618's story stops looking like an unusual embarrassment and starts looking like the ordinary life cycle of any scientific superlative. It won the title once, in 2004, with 66 billion. It may have quietly lost part of that title in 2019 to its own second measurement, and lost the rest of it at some undetermined point to a black hole in a cluster most people have never heard of. None of that makes TON 618 any less real or any less extreme. It just means the word biggest, attached to anything this far away, was never built to last. There's a reasonable question sitting underneath everything covered so far. It deserves to be asked directly instead of left implied. If astronomers have known about this uncertainty since at least 2019, why does 66 billion, the biggest black hole ever found, still show up confidently in videos, articles, and trivia lists made well after that? Part of the answer is simply how information ages differently in different places. A peer-reviewed paper revising a figure downward doesn't automatically update every website, documentary, or classroom slide built on the earlier number. Once a figure like 66 billion gets attached to a striking visual, an event horizon 40 times the width of the solar system, a number bigger than every star in the Milky Way combined, it becomes, functionally, a piece of internet folklore. Repeated because it's dramatic and specific, not because whoever's repeating it checked the 2019 literature first. The correction was published in an academic journal, read by other astronomers. The original number was published everywhere else, read by everyone. Part of the answer is also less flattering, and worth naming honestly rather than around bigger numbers travel better. The biggest black hole ever found is a cleaner, punchier claim than one of two disputed estimates for an extremely massive black hole, depending on which spectral line you trust. Nobody, making a thumbnail, chooses the second phrase even when it's the more accurate one. This video's own title borrows from the same instinct. the scariest black hole in the universe is a claim built for attention first, and the honest answer worked out over the last 2 hours turns out to be considerably stranger and arguably more interesting than the simple version the title implies. None of that makes the 66 billion figure fraudulent, or the people who repeat it careless. It makes it a case study in how a single, well-publicized measurement, taken at face value and never revisited by most of the audience that encountered it, can outlive its own uncertainty by years simply by being the version that got there first and said something bigger. None of tonight's open questions are permanently closed to better evidence. It's worth naming, honestly, what might actually change them. A new generation of extremely large ground-based telescopes currently under construction is being built with infrared instruments considerably more capable than anything Schemmer's team had access to. In 2004, designed in part for exactly this kind of problem, pulling a clean measurement of a redshifted line like hydrogen beta out of a faint, distant quasar without losing it in the atmosphere's own glow. If one of those instruments eventually remeasures TON 618's hydrogen beta line with modern precision, and the result lands close to Schemmer's original number, that would meaningfully strengthen the case for the larger mass. If it lands closer to what carbon-4 implied instead, the smaller figure gains ground. Either result would be more valuable than either existing measurement alone, precisely because it would come from an instrument built to address the specific weakness each of the earlier ones carried. The Phoenix cluster comparison could shift too, in either direction, as more clusters get surveyed with the same dynamical methods used there. A heavier confirmed record elsewhere would settle the biggest black hole question further away from TON 618 still. A challenge to the Phoenix measurement itself would reopen it. And the growth timeline puzzle? The question of how something this size existed within the universe's first 3 billion years stands to gain the most from an entirely different direction. Deep surveys of the early universe, hunting for more objects like TON 618 at similar or even earlier redshifts. The kind of search that has already turned up a small, growing family of oversized early black holes and shows no sign of stopping. None of that guarantees an answer arrives cleanly, or soon, or in a form simple enough for a single headline. But it does mean tonight's uncertainty is the ordinary, productive kind. The kind that points towards specific, buildable instruments and specific, plannable observations, rather than the kind that has genuinely nowhere left to go. There's one more way. An object like TON 618 leaves fingerprints on light, distinct from its own glow. It deserves a place in this investigation, even though it hasn't been the tool that measured anything covered so far. Any sufficiently massive object bends the path of light passing near it. A consequence of general relativity confirmed as early as 1919, when astronomers measured starlight visibly deflected around the sun during a total solar eclipse. Scale that same bending up to something with the mass of TON 618's black hole. Any light from a more distant galaxy happening to pass near enough would arrive noticeably warped, smeared into arcs, or duplicated into multiple images. A phenomenon called gravitational lensing that astronomers use elsewhere in the universe to detect and weigh massive objects that produce no light of their own at all. Nobody has reported a confirmed lensing signature from TON 618 specifically. Its extreme distance makes finding a suitably placed background galaxy, precisely aligned behind it, a matter of considerable luck, but the possibility sits there regardless, as a reminder that mass alone, regardless of whether an object glows, warps the space it sits inside enough to be detected by other means entirely. One more way, in principle, that something as violently invisible as a black hole still leaves an unmistakable mark on everything around it. Return, for a moment, to where this investigation actually stands, because it's easy, after this many detours, to lose track of what's settled and what isn't settled. TON 618 is a real, hyperluminous radio-loud quasar, first logged by accident in 1957, correctly identified in 1970 and 1976, sitting at a redshift of 2.219, roughly 10.8 billion years of light travel time away, in a part of the sky belonging to the constellation Canes Venatici. Settled. An accretion disk around its central black hole outshines the entire surrounding galaxy by such a margin that the galaxy itself is essentially invisible against the glare. Settled. A jet of particles, moving close to the speed of light, extends outward along the black hole's spin axis, and a vast structure of cold gas, spanning more than 300,000 light-years, sits aligned with that same jet, unsettled and likely to remain that way for some time. The actual mass of the black hole itself, caught between 66 billion solar masses from one spectral line and 40.7 billion from another, each measurement carrying a specific, documented weakness the other doesn't share, unsettled. Whether TON 618 is even the most massive black hole currently known, given a dynamically measured black hole in the Phoenix cluster that may already outweigh both of its disputed figures. Unsettled. Exactly how a black hole this size managed to exist within the universe's first 3 billion years at all. 3 settled facts. 3 real, ongoing disagreements. And underneath all 6 of them, a deeper question this investigation hasn't actually answered yet, and everything to do with what scariest was ever supposed to mean in the first place. It helps, at this point, to lay several threads from tonight side by side, not to close anything, but to notice how none of them, individually, actually settle the question this investigation opened with. A misidentified star, a radio signal that shouldn't exist, a redshift that placed an entire engine near the edge of observable time, an accretion disk outshining a galaxy it has rendered invisible, a mass measured once, then measured again, disagreeing by nearly half, a heavy arrival in an entirely different cluster, weighed by an entirely different method, a horizon large enough to be gentle rather than violent to cross, a cloud of gas 3 Milky Ways wide, aligned with a jet nobody has finished explaining, a timeline tight enough to strain the physics meant to explain it, and, underneath every one of those threads, a single object that has never once been seen, only inferred from light that left home before there was anyone anywhere to watch it leave. No one thread, alone, would justify the title this video opened with. Stacked together, they raise a harder version of the same question, rather than closing it. Which of these threads should even count towards scariest? And does the word survive being asked that precisely? Somewhere in the last 2 hours, the question quietly shifted. And it's worth naming the shift directly, rather than letting it pass unnoticed. If scariest means heaviest, the honest answer is that TON 618 may not currently hold that title at all. The object that likely does, the Phoenix cluster's black hole, rarely makes the same lists, mostly because 100 billion doesn't come attached to a decades-old catalogue number, and a story about a misidentified star. If scariest means closest, TON 618 doesn't come close to qualifying. There are black holes vastly nearer to Earth that would matter far more to anyone actually worried about proximity. If scariest means most violent, the accretion disk's raw luminosity is a stronger candidate for that title than the black hole itself. And the disk isn't the black hole. It's what falls toward one. If scariest means most likely to be photographed one day, TON 618 may be one of the least likely candidates on any serious list, precisely because of how far away it sits. What TON 618 actually earns, more convincingly than any single number attached to it, is a different kind of unease entirely. It is one of the most extreme objects ever identified using nothing but inference, stacked on inference, revised at least once already, and entirely capable of being revised again by an instrument that hasn't been built yet. The scariest part was never the number 66 billion. It was discovering how much confidence that number carried for how many years before anyone circled back to check it against a second method, and how readily an entire popular imagination adopted the biggest black hole ever found as settled fact, when the field itself had never actually settled on it at all. There's a quieter version of that same unease worth naming too. Most of what gets called knowledge about the deep universe works exactly this way. Whether or not a given object ever makes a dramatic headline, distant, unresolved, inferred from indirect evidence, carrying honest uncertainty that rarely survives translation into something short enough to repeat. TON 618 isn't an exception to how astronomy usually works. It's simply an unusually visible example of it, made stranger by how enormous the numbers involved happen to be. Sit with the timing one more time, because it deserves more than a passing mention. The light now arriving from TON 618 left its source when the universe was under 3 billion years old. Earth did not exist yet. The Sun did not exist yet. The material that would eventually become both was still spread thin across an unremarkable patch of an unremarkable galaxy. Not yet gathered, not yet warm, nowhere close to becoming anything that could one day build a telescope and point it outward. For roughly 10.8 billion years, that light traveled alone, crossing a universe that kept expanding the entire time it traveled, stretching the light's own wavelength further and further as the space it moved through kept growing beneath it. Walk the timeline forward from the moment that light left, the way you'd walk forward through any long story. Roughly 9 billion years into the light's journey, a cloud of gas and dust 11 billion years younger than the universe itself finally collapsed under its own gravity, and the Sun ignited. A few 100 million years after that, Earth finished forming out of the same leftover disk of material, cooling slowly from a molten ball into something with an ocean, and, eventually, something with a coastline. Life appeared, by the best current estimates, within another few 100 million years of that, then spent well over 3 billion years as nothing more complex than single cells, patiently before anything resembling an eye ever evolved to look upward at all. The light kept traveling through every single one of those chapters, indifferent, unhurried, already more than halfway through a journey that had started before any of them began. By the time any of that light reached a photographic plate in Tonensintla in 1957, it had outlived the death of stars that formed and burned out entirely during its journey. It had crossed the birth of our own solar system, the entire history of life on Earth, every war and every book and every named person who has ever lived, arriving finally as a single violet point too faint to notice as anything but routine, logged, numbered, and set aside as an unremarkable dying ember, because nothing about a point of light that faint suggested, to anyone looking at it in 1957, that it had already survived a journey longer than the age of our entire solar system. It is still arriving, tonight, at this exact moment, on instruments considerably more sensitive than a 1950s photographic plate, the same ancient light, still landing, one photon at a time, on a planet that didn't exist for the first third of its trip. Every black hole, according to theoretical physics, is expected to eventually end. Not through violence, but through a slow, almost imperceptible process called Hawking radiation, in which a black hole very gradually loses mass and energy to the surrounding vacuum over spans of time too long for ordinary language to hold comfortably. For an object of TON 618 scale, the numbers involved stop resembling anything a calendar was ever built to express. Current theoretical estimates place the evaporation timeline for a black hole this massive somewhere in the neighborhood of 10 to the 99th power years, a 1 followed by 99 zeros, a span so far beyond the current age of the universe that comparing the two is closer to comparing a single second to a length of time longer than a number can comfortably describe. Long before that clock finishes running down, every star currently burning anywhere in the universe will have gone dark. Every galaxy will have drifted far beyond any other galaxy's light, the universe itself will have entered an era physicists sometimes call the black hole era, when black holes like this one are nearly the only structures left with any mass at all. Nothing about that timeline threatens anything alive today, or anything that will ever be alive to notice it happening. It's offered here simply as the honest scale of the thing this entire investigation has been trying to weigh. An object expected to outlast every star, every galaxy, and very likely every form of intelligence the universe will ever produce. Evaporating so slowly that the end of TON 618 barely qualifies as an ending in any sense a human lifetime could recognize. None of tonight's astronomers, not Iriarte, not Chavira, not Ulrich, not Schemmer, not Gay, got to see the thing they were measuring. Every one of them worked from indirect evidence. A smudge on a photographic plate, the width of a single spectral line pulled out of light that had been traveling for longer than human civilization has existed. And every one of them, at some point, had to admit the limits of what that evidence could actually prove. There's something worth respecting in that, more than in the number itself. Schemmer's team didn't claim certainty. They published a method, a result, and the uncertainty attached to it, the way careful science always does. G's team didn't claim to have caught an error. They offered a second measurement, built on a different assumption, and let the disagreement stand in the open literature rather than forcing a false resolution. Neither team needed the other to be wrong for their own work to matter, which is a more modest, more honest way of doing science than the finality that headlines usually demand of it. The discomfort in this story was never really about a black hole being unusually large. It's about how much of what gets called knowledge, at this distance, is actually a best attempt, checked, rechecked, occasionally revised by half, and never quite finished. That isn't a weakness specific to studying TON 618. It's closer to the actual texture of frontier science in general, the part that rarely survives the trip into a documentary, a textbook, or a trivia night. Not a clean, finished answer, but a careful, provisional one, held loosely enough to be improved the moment better evidence arrives, and held firmly enough, in the meantime, to be worth publishing, teaching, and building the next measurement on top of. Spare a thought, for a moment, for what it actually means to spend a career on an object like this one. Every astronomer who has ever published a mass estimate for TON 618 has done so knowing, going in, that the number might be revised, contested, or quietly superseded within their own working lifetime. That a black hole this far away offers no way to simply go back and check the answer more carefully, the way a chemist might rerun an experiment on a lab bench. There is exactly one TON 618, 10.8 billion light years away. Every measurement of it has to be right the first time, using whatever instrument happens to exist at the moment someone points it there. Being wrong isn't a personal failing in a field like this. It's the ordinary cost of studying something this far past the reach of a second look. And yet the measurements keep coming, refined, contested, occasionally overturned, because the alternative, simply repeating the first confident number forever, never checking it against a second method, would be the more dishonest choice, not the safer one. Every astronomer named tonight chose the harder version of that trade. Publish something that might be wrong, clearly labelled with how it was measured and what it assumed, rather than say nothing and let an old number harden into false certainty by default. One more comparison. Before the last of tonight's threads pull together, the room holding you right now sits on a planet built from the same handful of elements every quasar's accretion disk is also built from. Hydrogen, mostly, along with the heavier elements, cooked inside stars that lived and died long before the sun ever ignited. Nothing about the atoms making up a hand resting on a blanket, or breath moving quietly in and out of a chest, is separate from the physics running this entire investigation. The same gravity holding a body against a mattress is a weaker, gentler cousin of the gravity that made this whole 2 hours necessary in the first place. One force, one set of equations, doing something almost imperceptible here and something almost unthinkable 10 billion light-years away. That's not a coincidence built for comfort. It's simply what it means to live inside the same universe as something like TON 618. The physics doesn't stop being true just because the scale changes. A body at rest and a black hole 66 billion times heavier than the Sun are being described. Underneath everything, by the same handful of equations, solved for wildly different numbers plugged into the same variables. Nothing about that closes the distance between here and there. It just means the distance was never actually a wall between two different kinds of reality, only a difference of scale inside one continuous, indifferent, entirely explicable set of rules. So, is TON 618 the scariest black hole in the universe? Not, honestly, because it's the heaviest one confirmed. That claim, if it belongs to anyone right now, likely belongs to the black hole quietly sitting in the Phoenix cluster, measured by a method nobody argues about. Not because it's the closest or the most dangerous to anything alive, because at 10.8 billion light-years away, it has never posed a threat to anyone or anything. And not because the number 66 billion is uniquely, permanently true, because it isn't. It's one of two defensible answers to a question astronomers still haven't closed. TON 618 earns its reputation somewhere else entirely, in the sheer distance between what's known and what's merely inferred, in an object bright enough to outshine its own galaxy, yet never once photographed directly, because no instrument built or planned can resolve it, in a mass estimate that swung by nearly a factor of 2, 15 years apart, using two different lines from the same unresolved point of light, in a black hole that, whichever number turns out to be true, could theoretically be crossed without feeling a thing. No violence, no warning, just a threshold quietly closing behind you, in a structure of cold gas 3 Milky Ways wide, aligned with a jet first noticed by accident in 1970 that nobody has finished explaining, and in a timeline that places all of it within the universe's first 3 billion years, a schedule tight enough that astronomers still argue, honestly, about how something this size had time to exist at all. Stack those pieces together, and a different kind of monster comes into focus than the one the title promised. Not a single number, sitting quietly at the top of a list, daring anyone to imagine it. A moving target revised once already, contested between two legitimate methods, dwarfed in raw mass by at least one rival measured a completely different way, wrapped in a cloud of gas nobody has finished explaining, sitting at a moment in cosmic history that strains the physics used to explain how it got there at all. Actually holding all of that at once, rather than reducing it back down to a single, frightening number, is a harder, stranger, more honest kind of scared than the title alone lets on. The most unsettling thing about TON 618 was never its size. It's how much of that size still depends on trusting a measurement made from 10 billion years away, of a thing no one has ever actually seen, and how comfortable an entire species got repeating a number as settled fact, long before the people who found it ever called it that themselves. Go back, one last time, to that photographic plate in 1957, to a violet point of light filed under a number instead of a name. Nothing about the plate changed between then and now. The same faint, unremarkable dot still sits exactly where Iriarte and Shavira found it, indistinguishable, to the naked eye, from 100 other dim points logged in the same survey. What changed is everything that's since been read out of it. A radio signal that shouldn't exist for a dying star. A redshift that placed it near the edge of observable time. Two competing weighings of a black hole that may or may not be the heaviest ever found. A cloud of gas wider than 3 galaxies. And a question about how anything gets that large that quickly that still doesn't have a finished answer. A dead star was never the file this belonged in. What actually sits behind that violet point is closer to the opposite of dead. An engine that has been running and reshaping the space around it for for longer than most of the universe has existed, still burning, still sending its light outward in every direction at once, entirely unaware that a small blue planet, running on the leftover material from stars that finished burning ages before this light ever left home, spent 2 hours tonight trying, one measurement at a time, to weigh something it will never get to see. Iriarte and Chavira never learned any of this. Their survey moved on to entry 619, then 620, cataloguing faint blue points by the thousand, filing each one under the best explanation their era had available. Neither of them lived to see a radio dish in Bologna prove their dead star wrong, or a spectrograph in Texas prove it stranger than wrong, or an array of dishes in a Chilean desert reveal a cloud of gas 3 galaxies wide sitting quietly around it. That's simply how most careful, patient scientific work actually unfolds. Not as a single triumphant discovery, but as one entry in one catalogue, filed correctly by the standards of its own moment, waiting for a question nobody involved had any way of asking yet. Somewhere in an archive in Mexico, the original plate, or a scan of it, likely still exists. A small rectangle of glass or film, decades old, holding a point of light that has since been the subject of radio surveys, spectrographs, 2 competing mass estimates, an entire millimeter wave array in the Chilean desert, and now, tonight, one more attempt to hold the whole story in a single sitting. The plate itself never had an opinion about any of that. It simply recorded what arrived, the way every honest instrument does, and let 6 decades of better questions slowly decide what the recording actually meant. That's the quiet thread running under everything covered tonight. More than any single number. Not that the universe hides its most extreme objects behind deliberate mystery, waiting to be unveiled. Just that some of them arrive looking exactly like something else entirely, filed correctly under the wrong idea, until an instrument good enough, or a question patient enough, finally comes along and asks the plate to explain itself again. The universe will still be here when you wake up. So will we. Good night.